We've talked about quantum advantage in past episodes as an idea. Today, we're going to dive a little deeper to a recent experiment that provided a thousandfold boost in speed. And this isn't a theoretical problem. It's real portfolio optimization with a real edge provided by D-Wave's hybrid classical quantum system. Is 2021 the year for advantage? Find out in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is CTO of a company called Multiverse, which is a great name if you're into the many worlds interpretation of quantum mechanics like I am. He's working on something pretty cool, basically bringing quantum computing use cases to finance, and that's near and dear to my heart. So I'd like to welcome Sam Mugel.
Thanks, Konstantinos. It's a real pleasure to be here.
Yeah. So glad you can make it. Why don't you tell us a little bit about your company and the disruptive work you're doing in finance?
Great. Yeah, with pleasure. So we are a startup, a fintech startup, and we're using quantum computing to give an edge for Fortune 500 companies that want to gain an edge through like really deep technology, basically. And so we're using an awful lot of techniques from quantum computing, from deep physics, and yeah, applying these to real industry relevant problems. So I'll be really thrilled to tell you a little bit more about that afterwards.
Yeah, that sounds terrific. You guys started as a non-for-profit, right?
Yeah, that's correct. Actually, so 4 years ago, Multiverse started out as a WhatsApp group. We weren't called Multiverse at the time. We were called Quantum for Quants. And we had all these contacts over in Europe that were asking us about what is quantum computing? How worried should I be about it, basically? And so we set out with this company to answer exactly this question and publish a few like scientific articles. And in one of these, we really dive deep and looked at every single quantum computing algorithm and tried to say, how can this be relevant for finance? Where can it bring an advantage? And by the time we'd done this homework, we'd identified the real like low-hanging fruits that could be developed today with current hardware. And basically, we were just like, why is nobody doing this? You know? So we incorporated as a company. That would have been almost exactly 2 years ago. And yeah, we were approached by Creative Destruction Lab, and so now we've got a foot in Toronto as well. And we've been developing like really killer quantum applications ever since.
Yes, you guys are working in optimization and quantum machine learning, right? Basically.
That's right. So quantum optimization was really the low-hanging fruit first use cases for finance that we identified. And I'll be telling you a little bit more about that afterwards. Quantum machine learning is a much more like ambitious project that we're starting to dig our teeth into at the moment, and there's some really interesting stuff that you can do over there in terms of like fraud detection. There's a lot of like open problems for in finance, and also in terms of things like credit scoring. I mean, yeah, there's a lot of like billion or $trillion verticals over there. And another one would be life insurance and just estimating how to price these things. Like, there's a lot of really interesting stuff that can be done.
Yeah, it sounds like we're working on a lot of the same things, actually. Yeah, the fraud detection, we're actively doing that right now. Yeah, it's going to have a huge impact, of course. And I think we're going to see examples of that in just some of the stuff you've already done. And I wanted to have you on because I found your work really, really impressive. And not to get too far ahead of ourselves, but I kind of think of you as one of the front runners, as someone who might prove quantum advantage. But, just saying, I don't know.
I hope you're right.
Yeah. I wanted to have you on, when, like I knew him when, that kind of. So, Ed, did you want to talk a little bit about like why computing can be accelerated by quantum and why quantum computing is relevant to finance in particular?
Yeah, absolutely. Basically, let's see. The way that I like to explain this is that so in regular computing, you have your bits that can be 0 and 1. Or 0 or 1, and then you apply all these binary operations to them, and this allows you to perform computations, essentially. In quantum computing, your smallest unit of information, your quantum bit, can be also 0 and 1 at the same time. And so this is analogous to how Schrodinger's cat, for instance, can be dead and alive simultaneously. So this is really part of the quantum weirdness, like the weird quantum properties of our world. And the interesting thing for computing is that when you apply an operation to your quantum bit, you're simultaneously applying it to both states. So if I apply an operation, a not operation to my quantum bit, for instance, I'll be performing the not on both states simultaneously. And so you can already see that quantum computing gives you really naturally access to parallel computing, whereas in classical computing, you have to have dedicated hardware to do this, basically. The other interesting thing is that the amount of states that are available double every time I add a quantum bit. And so by the time that I have 330 quantum bits, I can perform more operations simultaneously than there are atoms in the visible universe. So this immediately tells you that quantum computing gives you access to computational resources that would be completely impossible classically.
Yeah, I try to get that across. Like we're almost to the point where you can't simulate the processors that are being developed now. And then maybe next year we'd have to turn the entire planet Earth into a classical computer to simulate them. So I try to get that across. Yeah, it always baffles people. So I really love that. That chart that you can visualize for how quantum computing is increasing so rapidly. So it is time to take advantage of it. So for finance, we do end up using with big data sets, right? So that's where some of the biggest advantage might come in. Absolutely.
There's actually a real problem in finance and data science in general, which are we're a lot better gathering and storing information than we are at processing it. We're arriving to the end of Moore's law at the moment, and so we're gathering this exponential amount of information, but the amount of computational resources that we have at our disposal is starting to stagnate. And so there's a real problem for like huge banks, for instance, that turn around and say, hey, we've got all this data now, how can we get value out of it? And here there's a real hope that quantum computing will help these big institutions to address that problem.
Yeah, and in the short term now, in this like near term, it seems to be that we have a real shot at doing it in a significantly better way using annealing, right?
Mm-hmm. Yeah, so quantum annealing is really a fantastic analog computing tool for optimization problems. It's one of the first examples of quantum computing that we've had. And essentially it's not, you wouldn't think of it as a general purpose computer. It's really a computer that natively solves optimization problems, which are everywhere in finance.
Yeah, that's an important point. And you guys applied the D-Wave annealer to something that is really what led to this episode. So I definitely wanted to get to that. So you did a BBVA case study, right? Or a use case?
That's right. So we were working with the capital markets team on portfolio optimization applications. So BBVA that we were working with is the world's 47th biggest bank, so quite a major entity. So we were really thrilled for this opportunity to work with them. And we decided on portfolio optimization because it's a very, very difficult problem for classical computing. It grows exponentially with the number of assets or the number of time steps you might consider. And also it's a nice problem because it's applicable in many, many areas in finance. You can apply it to backtesting, you can apply it to index tracking, you can apply it to stress testing portfolios. So there's a lot of really exciting high value applications there. And so the problem that we solved with BBVA was given forecasts about market data, what would be the optimal portfolio taking into account transaction costs? And so essentially we'd have to determine the optimal investment trajectory. And so taking into account transaction costs and taking into account risk of the portfolio exactly. And this was a really staggeringly difficult problem for a classical computer.
And what blew my mind was normally when you're doing like a POC, you start small, you get a small set of data just to kind of like prove that you can do it, and then you try to extrapolate. You guys decided, nah, we're going to get like the biggest data set on planet Earth and go that way instead, basically, right? So you guys use what the XXL data set. So did you want to talk a little bit about the implications of that data set size?
Absolutely, yeah. BBVA really dropped us in the deep end. So we were the biggest data set we considered, though we called the XXL data set, was 4 years of data with monthly rebalancing. So an awful lot of potential trajectories. And we were considering, I believe we were initially given 54 assets, and we used some really sophisticated like clustering methods to determine 8 most representative assets. And so the final portfolio we considered was 8 assets. We had some constraints on how much we would be able to invest in each asset, and then over 4 years of data. And I believe this came down to, I think it was 10 to the, I'd have to double check. I think it was 10 to the 400 possible solutions. So way more than there are atoms in the visible universe.
Yeah, way more. It's like 10 to the 90 or something like that.
Yeah.
So that started to show the limitations of classical, right? Because you guys were comparing the same approach to using TensorFlow.
So we compared several methods. One of them was a standard library in Python for optimization called Gecko. We did not consider TensorFlow, but we did look at tensor networks methods. That are some in-house algorithms that we developed, and we also run on the side some like hybrid quantum computations on IBM's chip.
That's right. Yeah,
Yeah.
I remember.
And here D-Wave actually had a little bit of a leg up because it's the problem that's natively solved by that particular QPU. And what we found was that really rapidly, we got into problem sizes that even Gecko standard libraries or some exhaustive solvers that we coded ourselves, and also the IBM chip, just could not even begin to consider. And the only two solvers that were actually able to solve this XSL dataset were our Tensor Networks applications and the D-Wave solver. And the interesting thing is that while our Tensor Network solver tend to converge to a slightly better solution, this would generally take about a full day of having the computer running to get results from this, where it took the D-Wave quantum computer 170 seconds.
Yeah, that was the moment for me. I was like, whoa, wait a minute.
Yeah.
So we're taking a practical size of data. We're doing it in 170 seconds instead of a day. And the accuracy wasn't really that far off, right? I mean,
it wasn't that far off. I think we got so we were looking at, our metric was the Sharpe ratio, which is a ratio of returns to risk, basically. And Sharpe ratio of 8 is generally considered to be like risk-free, like unheard of investment. And I think we were getting to Sharpe ratios of like, I'd have to double check, but I think it was 12 with D-Wave and up to like 14 or 16 with Tensor Networks. So like staggering performance.
Yeah, I couldn't believe how close it was. Yeah, I think it was like, I wrote it down somewhere. It was like 12.16 for D-Wave and 15.83 for Tensor. And it was,
okay.
I was like, yeah, so if you've got that and the timing, how is this not the approach to, a form of supremacy, right? A form of advantage. We're like edging along here. And did you want to talk a little more about tensor network algorithms and?
Great, yeah. I'll tell you a couple of words on them. So basically, these are classical algorithms, but they're borrowing ideas from quantum information theory. So the idea here is that we're going to borrow ideas that tell you where the information content is in the problem, and this can really boost the performance of classical computing algorithms. So there's lots of interesting work in applying this to machine learning. We're doing parts of that work. Another big player in this domain is Google. In this particular use case, we were really using it to try to figure out which parts of solution space should we be focusing on, basically. So the analogy here is, imagine that you want to find the lowest point in a chain of mountains, and then you've got a smart method, in this case Tensor Networks, to tell you where all the valleys are, and then you don't have to bother about exploring all the peaks. You can just bother exploring all the valleys, basically.
Interesting. So is it strategic to still develop tensor network algorithms?
Absolutely. Yeah, basically for us, our clients don't really care about how we get to a solution. What they want to know is that we've given them the best solution the technology can provide, right? Mm-hmm. And when you're in really early stage, like quantum computing like this, it's really nice to have a method to push classical computing to its absolute limit. And additionally, it also tells you what classical computing can do well. And so then we can just isolate that nugget of bottleneck problems and then shoot all that off to the quantum computer and then just and solve everything we can classically using tensor networks, basically.
Yeah, I think it's that hybrid approach, that like doing it in pieces, that's going to give us our first real benefit to using quantum in any way, shape, or form.
Mhm.
I think that's how we're going to get our short-term gain. Basically, would you agree that?
Absolutely. Absolutely. Yeah, I think you're absolutely correct. I think that being able to being able to use classical computing, that's very good for what you can use it, and then just solving the really hard stuff on quantum computers absolutely is the key to advantage. I think another key to it would be to use analog platforms. I see a lot of promise in these short terms. So things like D-Wave or Xanadu or Pascal, these are all quantum computing startups that are developing analog quantum computer. And the logic here is that these machines solve a problem natively, whereas machines that attempt to be universal are bothering with approximating gates and qubits, and all this adds errors and reduces coherence times, basically.
Yeah, so I think in the short term, it'll be the time for those machines to shine, right? Like this will be like the glory years for 2 years or so. And then everyone's going to be distracted when we're starting to see advantage in universal gate-based machines, which will...
Yeah, I totally agree to this. I think short term, like we're going to see some really impressive performance from analog machines, and amongst which quantum annealers. I think long term, when we have a like universal error corrected gate model computer, then they're going to be able to do everything that the analog machines do, and so probably people will leave aside the analog machines, but I don't think this will be before well into 2030s. So there's probably some really exciting results to be had already now from analog machines.
Yeah, it's time to really use our D-Wave, monthly credits, right? It's time to cash them in.
Couldn't agree more.
So do you think, and I want to talk about another study you guys did, but would you say that the BBVA one has a good extrapolation somewhere in it of when we'll have advantage? Do you see like something you can tweak to get us even closer, like better accuracy, even faster, something that could really throw a stake in the ground?
Wow, this is such a loaded question.
Yeah, I want controversy. I want everyone to like criticize us after we're done with this.
So I'm going to say yes and no. Like the reason why I say no is that for me, advantage is really simultaneously a practical and mathematical problem. The really difficult mathematical question here is, can you prove that no classical algorithm could give you this performance in a reasonable amount of time? Like the typical example would be factorizing really large numbers, right? Mm-hmm. Okay, so maybe you can do this a lot faster on a quantum computer, but can you prove that you couldn't do this with the same performance on a classical computer? And this is very hard to do, because all we know at the moment is that we know that we don't have an algorithm to classically efficiently factor large numbers, but it's very difficult to prove that this isn't possible, right? So in that sense, I'd say that our study is not sufficient to bring us closer to quantum advantage. However, I'd say that it is a huge step in the right direction, and this is my yes, that we've shown that quantum computing can outdo known methods for a really difficult problem, which is this portfolio optimization problem. And the nice thing is we've shown this on a very like practical and valuable and tangible problem. And additionally, one for which like the classical alternatives for this are not actually that good for optimizing these problems that have no nice mathematical structure. Typically, like people would use heuristical algorithms for this type of thing, and and these algorithms don't generalize very well. What's nice about quantum annealing is that there's actually mathematical proofs that this will theoretically converge to the optimal solution. So I think this is really the nice result of our study, that we've been able to outdo like standard classical methods and on a very like practical problem.
Yeah, I agree. It's the practicality, right? Who cares if we can make up something, run it, and say, look, it's better, kind of like what they did in China with that like photonic system. It was a completely useless problem, but they proved that it can do it,
Exactly. This is the typical thing of like, oh yeah, a quantum computer is just so much better simulating being a quantum computer than a classical computer.
Yeah. I mean, going right back to Feynman, that was the whole point, I guess, like to simulate. But this way we have something usable. And the other distinction is once we achieve something that seems like advantage, the quantum computer is going to get just a little better. And as we've already discussed, a little better means a lot better, right? Like add a few qubits and then, whoa, it's a lot better at doing it. So it's sort of like the thing that once it takes off, it just keeps taking off.
Absolutely.
So and there won't be neck and neck.
There's a real social advantage to this as well. Like think of like classical computing got to where it is. Sorry, I'm taking you completely off topic.
Oh, no, it's fine.
Classical computing got to where it is because there's many trillions that have been invested in the silicon industry. And once quantum computing can show that it can catch up to that, then I think we're going to start seeing similar investments in the quantum computing industry as well.
Yeah.
So I think once it goes a little way, then it's going to go fast.
And it's just a simple comparison of lines on a graph. Like Moore's law looks one way. Quantum is going to look very different, and it's not going to be neck and neck ever. So I think in a few years, you're like the types of things you did already with like Bankia, it's going to be with BBVA and Bankia, it's going to be just completely different. It's going to just shoot straight up in like a line, like a skyscraper.
I think so, yeah. Because so this thing of like you're doubling your resources every time you add a qubit, this is telling you that if you want to keep up with Moore's law in quantum computing, all you have to do is add one single quantum bit every 2 years.
Yeah, I know. That's not very difficult to pull off.
Yeah,
that's why it's so exciting. Yeah. So did you want to talk at all about what you guys did at Bankia and how it was different?
Great. Yeah. So here we were building upon the study that we did with BBVA. So still dynamic portfolio optimization. And the difference here is that we weren't taking into account transaction costs. Instead of that, we were looking at a minimum holding period. And this made our problem. So essentially something that says, if I buy an asset now, then I need to hold it for at least, in this case, 7 days into the future. And this is a very standard constraint for banks. And this is what made our problem very, very difficult. Because it means that your investment today, your optimal investment today is highly dependent on your optimal investment yesterday and the day before that. And the other way in which it was different is there was sensibly more data. We were looking at a portfolio with 10 to the 1300 possible possibilities. So we were in a whole other league.
Oh, yeah, that's such a painful number. Would any of this then be considered impossible to solve with classical? To some degree, let's see. I think I actually honestly don't know of any classical method that would be able to deal with that amount of variables. So we're actually in the process of taking benchmarking a step further at the moment, and we're benchmarking our optimization algorithms against a bunch of like industry standard, like
models that you need to pay for. And so I'll have a more complete answer to this question in the future.
Nice.
But I think to take you back up on this, I think that there's two things that made this problem either impossible or close to impossible on classical computers. One of them is the sheer size of the problem, and the other one is that we were accounting for risk exactly in this problem, which is incredibly difficult to do with this type of problem. People usually take all kinds of shortcuts to avoid accounting for risk exactly.
So I don't know. So far, everybody heard it here. We've got something possibly impossible to solve. We've got, the speed. It's all sounding good to me. I don't know. Did you want to talk at all about, so this is a huge amount of data, anything that was involved in like optimizing it, post-processing, that kind of thing?
Sure. So we, maybe this is entering a little bit into the technicalities of it, but we did something that's quite fun in this case, is that, so we were solving this again with D-Wave quantum computer, and D-Wave's quantum computer can handle a certain type of optimization problem, which is a quadratic optimization problem. So you can only enter functions of a certain kind into your QPU, basically. And in this case, we used a hybrid approach that allowed us to go further than this, basically, and to optimize a problem that was more complicated than quadratic, that had higher order terms. So I think the highest order terms that we had in this case were to the power of 7 instead of to the power of 2. And the way we did this was we managed to break up our problem into many different parts and solve these independently, and then run a post-selection algorithm that, due to the size of the problem, would have usually taken an awful lot of time to do this. But we played a few tricks to actually exponentially reduce the complexity of the problem. And it's very difficult to explain without showing you a diagram. Mm-hmm. However, I refer you to the paper that we brought out in 2020 in collaboration with Bankia. It's available on our website, and it's all explained in a lot of detail exactly how we did this.
Yeah, absolutely. And I will, of course, include any links you want in the show notes.
Fantastic.
No problem there. And so you guys went through a process of selecting the right types of problems to work with these customers to show real potential gains here. So to our listeners, some of them from company, maybe financial services, how would they go about picking what's a good use case for trying to?
Okay, this is a great question. I think a good use case really needs to, for quantum computing, really needs to gather 4 points, basically, to meet 4 conditions. The first one is you want this to be a very high value problem. There's quantum computing right now is very expensive, and there's no sense in developing a solution that uses quantum computing if you can't justify the use of quantum computing, basically. So you want this to promise high returns. You want your inputs to be quite small, and the reason for this is that we're still very limited in the number of quantum bits available. So for reference, IBM's latest quantum computer was around 50 qubits, I believe. D-Wave's was 5,000. But compare that to your gigabytes or terabytes of computing of amount of bits that your computer has, right? So you want it to have small inputs. You want there to be many intermediate states, because this is really where quantum computing shines. They can explore all of these states at once. And ideally, you want your best classical alternative to be really, really bad. Like, the best case scenario is the best solution you can get is by brute forcing the problem, and then you're really in business. You can find potentially like a quantum algorithm that could do this more efficiently.
Yeah, and that was sort of, I guess, one of the first appeals of the Grover's algorithm. Yeah, instead of n divided by 2, we're talking about square root of n. So that's a huge difference in search.
Precisely, yeah.
Yeah.
Yeah, this is a really good example of if you're looking for an item in a list, there's no way around it. You have to look at every item in the list until you find the item you're searching for. So this was the first like really big win for quantum computing, to be able to show that there was, in the quantum world, there was a way to build an algorithm that didn't have to brute force this problem. Yeah.
Absolutely. Yeah, that's a very simple example. And it sounds like, to any companies listening, these criteria exist in a lot of things you're doing right now. So it should be pretty easy to start identifying what you can apply these machines to. And I know we touched on it numerous times throughout here, but did you have any other thoughts on this whole idea of advantage, and when all of a sudden the industry is going to realize that, wow, this is it. There's no going back.
I think that Google already demonstrated a flavor of advantage on their QPU back in 2019, I believe, and like you said, a Chinese group demonstrated it more recently. But I think the slightly disappointing thing for like people like me, at least, that are very conscious of the use of quantum computing in industry, is that these were not for a particularly useful problem, right? Google managed to select a problem where they were able to show, like, they built a problem for the purpose of it being able to be solved faster on a quantum computer than on a classical computer. I believe it was information scrambling. So I don't think, off the top of my head, I can't think of any industry applications. But I think that very soon, like, now that we know that these problems exist, I think very soon we're going to be able to demonstrate actual quantum advantage on useful problems. And I think from there it's going to go very fast. I think many groups are going to be able to show this, groups and startups, and obviously, like, at Multiverse, we partner with many hardware providers, from like IonQ to D-Wave to Xanadu to Pascal and IBM, and they've all got like extremely exciting machines lined up to come. So I think that we'll soon have many more realizations of quantum advantage on useful problems.
I'm going to throw a stake in the ground right now and say I think we'll have it by Christmas. What do you think?
Yeah. Okay. I'll take that bet with you. I'll be with you on that. Quantum advantage on a useful problem by Christmas. Perfect.
I think that's what we all want in the industry under the tree. That's going to be what we want.
And I think that would definitely make 2021 a really memorable year, right?
Yeah, I know, something to turn this around a little bit. Yeah, I think that's what's going to happen. So as we're all, sweating, because this is going to air now, it's going to be summer, we'll all be thinking about a cozy Christmas with quantum advantage under the tree. So yeah, thank you so much for coming on. I really enjoyed this, and I hope we can cross paths numerous times and work on something amazing one day.
Absolutely. Thank you so much for having me. It's been really fun.
That does it for this episode. Thanks to Sam Mugel for joining today to discuss multiverse computing and their financial use case. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also find information on our quantum services at www.protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.